Welcome to our today's lesson. In our today's video, we are going to design a composite floor incorporating profiled metal decking. The question says, the figure below shows a part plan of a composite floor measuring 9 meters by 6 meters. The slab is to be constructed using profiled metal decking and normal weight grade 35 concrete and is required to have a fire resistance of 60 minutes. The longitudinal beams are of grade S355 steel with a span of 9 meters and spaced 3 meters apart. Design the composite slab and internal beam assuming the floor loading is as follows. The imposed load 4 kilonewtons per square meter, partition load 1 kilonewton per square meter, weight of finishes 1.2 kilonewton per square meter, weight of sealing and services is equals 1 kilonewton per square meter. The density of normal weight reinforced concrete is 24 kilonewton per cubic meter. Slab design. Assuming the slab is unpropped during construction, use table 4.17 to select a suitable slab depth and deck gauge for the required fire resistance of 1 hour. It can be seen that for a total imposed load of 7.2 kilonewton per square meter, that is occupancy, partition load, finishes, ceilings, and services, and a slab span 3 meters, a 125 millimeters thick concrete slab reinforced with A142 mesh and formed on 1.2 millimeters gauge decking should be satisfactory. And now we can dive into solving our today's problem. Thank you. Welcome. We are going to begin with calculation of the design load, which will help us to determine the value of the design moment. Therefore, the design load will be given by 1.4 multiplied by the effective thickness of the slab times the density of concrete plus the weight of the finishes. So we add the weight of the finishes, which forms part of the dead load, plus the weight of sealing and the services. Therefore, plus sealing and services multiplied by the span, which is the beam spacing, L. This should be added to 1.6 into the imposed load, plus the partition load, which forms part of the live loads. So we add partition load, and then the same way we multiply by the beam spacing, that is 3 meters. From manufacturer's literature, the effective thickness of slab is usually given by the depth of the concrete slab minus 26 millimeters, and the depth of the slab is 125 millimeters. We subtract 26, and that is going to give us 91 millimeters. Therefore, the design load W will be equal to 1.4 into effective thickness of the slab, which will be 91 divided by 1,000. We convert millimeters to meters. 1 meter is equivalent to 1,000 millimeters. Therefore, this is going to be equal to 0.91 meters. So 0.91 multiplied by the density of concrete, 24 kilonewtons per square meter. Then we add the weight of finishes, which is 1.2 kilonewtons per square meter. Then we add these two, the load of sealing as well as services, which is 1 kilonewton per square meter. Then we multiply this by the beam spacing, which is 3 meters. This one we are going to add to 1.6 into the imposed load, which is 4 kilonewtons per square meter, plus the partition load, which is 1 kilonewton per square meter. And then we multiply by the beam spacing, which is 3 meters. This is going to give us a design load of 42.4 kilonewtons per meter. Therefore, the design load W is 42.4 kilonewtons per meter. Then from there, we can now determine the value of the design moment. And therefore, the design moment, that is M. Design moment will be given by WL squared divided by 8. That is for a beam that is subjected to a UDL over its entire span. Therefore, the design moment will be equal to W, which is the design load, 42.4 kilonewtons, 42.4 kilonewtons times the beam span, which is 9 meters, therefore 9 squared. We divide this by 8. And by doing so, we are going to get a design moment of 429.3 kilonewton meter. Therefore, that is the value of the design moment. Design moment is equals 429.3 kilonewton meter. After getting the value of the design moment, the next part will be calculation of the effective width of the concrete slab. Therefore, effective width of the concrete slab, that is BE. The effective width of the concrete slab, BE, is the lesser of 1 L divided by 4. That is the beam span divided by 4. So that is 9 meters. We convert to millimeters. We multiply by 1,000. So this is going to be 9,000 divided by 4. And 9,000 divided by 4 is 2,250 millimeters. Or BE, the effective width of the concrete, will be equal to the beam spacing. Beam spacing. And in this case, beam spacing is 3 meters, which when converted to millimeters, that is 3,000 millimeters. And therefore, the least between the two is 2250 millimeters, which will now be the value of the effective width of the concrete slab. And therefore, BE that we are going to be using will be equal to 2250 millimeters. After getting the value of the effective width of the concrete slab, that is BE, we are now going to determine the value of the moment capacity. Therefore, we go to moment capacity. Moment capacity. And before we determine the value of the moment capacity, we are going to use trial and error to select a suitable UB steel section, which we are going to test whether it will be suitable or not. And therefore, we are going to say using trial and error, try. So we are going to try this UB section, a UB section of serial size 305 by 165 by 40 universal beam steel section. So this is the section that we are going to try and see whether it will be suitable for the tests that we are going to subject it to. And this UB section will be of grade S355 steel, grade S355 steel section. Then after choosing or selecting a section by use of trial and error, we are going to determine the resistance of the concrete flange. So we go to resistance of concrete flange. And resistance of concrete flange is usually denoted by RC. RC will be given by 0.45 multiplied by the characteristic strength of concrete, that is FCU, multiplied by the effective width of the concrete slab, which is BE, multiplied by DS minus DP, whereby DS is the depth of the thickness of the slab, and DP is the depth of profiled metal decking. And therefore, the resistance of concrete flange will be equal to 0.45 multiplied by the characteristic strength of concrete, which is 35 newtons per square millimeters. We multiply this by BE, which is 2250 millimeters, into DS, which is 125 millimeters, minus DP, which is 55 millimeters. We are going to multiply this by 10 raised to the power of -3 to convert RC from newtons to kilonewtons. And therefore, this is going to give us a resistance of concrete fringe a resistance of 2480.6 kilonewtons. Therefore, that is the resistance of concrete fringe, RC. After getting the value of RC, we are now going to determine the value of RS, that is the resistance of the steel beam. So we go to resistance of steel beam section, which is denoted by RS. And in this case, RS will be given by APY, whereby A is the area of the steel section that we have selected, and PY is the design strength of steel. That is, since the steel section we have selected is in the grade S355, the design strength of this steel is going to be 355 newtons per square millimeters. Therefore, from Appendix B of the BS 5950, the area of this universal beam section is 51.5 square millimeters, square centimeters, 51.5 square centimeters. We need to convert that to square millimeters. So you are going to multiply by 100, that is 10 squared, since 1 square centimeter is equivalent to 100 square millimeters, or 10 squared square millimeters. Then we multiply by the characteristic, the design strength of steel, which is 355. We are going to get the answer in newtons. And since we want the answer in kilonewtons, we are going to multiply by 1,000 raised to the power of -3. That is, we are going to multiply by 10 raised to the power of -3, or divide this calculation by 1,000. And by doing so, we are going to get RS being equal to 1,828.3 kilonewtons. So that is the resistance of the steel beam. So when we compare RC, which is 2480.6, and RS, which is 1828.3 kilonewtons, we find that RC is greater than RS. And that means that the plastic neutral axis will lie within the slab. And we can prove that by substituting the value of YP, or determining the depth of the plastic neutral axis using this formula. YP, which is the depth of the neutral axis, is given by APY divided by 0.45 FCU multiplied by BE, which is the effective width of the concrete slab. And therefore, YP will be equal to APY, which is RS, that is 1,828.3 kilonewtons, divided by 0.45 times FCU, characteristic strength of concrete, which is 35 newtons per square millimeters. We multiply this by BE, which is 2250 millimeters. 2250 millimeters. This RS is in kilonewtons. We have to convert it to newtons. That is multiplying kilonewtons by 1,000. Therefore, we are going to have APY, which is 1,828.3 times 10 raised to the power of 3, which is 1,000. And by doing so, we are going to get the depth of the neutral axis being equal to 51.6 millimeters. When we compare this by ds minus dp, which is ds is 125 millimeters and dp, the depth of profiled metal decking, is 55, which is going to give us 70 millimeters. We find that since yp, which is 51.6 millimeters, is less than ds minus dp, which is 70 millimeters. Therefore, it means that the plastic neutral axis is lying within the slab. After determining that, we are going to now calculate the moment capacity. Moment capacity of the composite section. And because yp is lying, or the neutral axis is lying within the slab, the formula we are going to use to determine the moment capacity will be mc is equals rs into d, that is the depth of the ub section from appendix B of BS 5950. We divide that by 2. Then we add this to ds, the depth of the concrete slab, minus rs divided by rc into ds minus dp divided by 2. Therefore, that is the formula we are going to apply to determine the value of the moment capacity of the composite section. Therefore, MC will be RS, which in this case is APY, that is 1,828.3 kilonewtons. We convert to newtons, that is multiplying it by 1,000, into D, the depth of this UB section, that is 305 by 165 by 40, from appendix B of the BS 5950 is 303.8 millimeters. We divide this by 2. Then we add this to DS, which is 125 millimeters. 125 millimeters. We subtract RS over RC. RS is 1828.3 kilonewtons. We convert to newtons, that is multiplying by 1,000. Divide this by RC, which is 2480.6 kilonewtons. We also convert it to newtons, therefore divide that by 2480.6 times 10 raised to the power of 3, which will be multiplied by ds minus dp, that is ds 125, dp 55, divided by 2. So for us to get the moment capacity in kilonewtons meter, we are going to divide the whole of this calculation, or the answer, by 1,000,000. Since 1 kilonewton meter is equivalent to 1,000,000 newtons millimeter. So we are going to multiply this by 10 raised to the power of -6, which is the same as dividing by 1,000,000. And by doing so, the moment capacity MC will be equal to 459 kilonewton meter. Kilonewton meter. That is the moment capacity of the composite section, MC. Now, this moment capacity should be greater than the total moment. And in this case, the total moment is given by the design moment plus moment due to self-weight of the UB section. The design moment, we got it here, 429.3 kilonewton meter. So what we are going to calculate is the moment due to self-weight of the UB section. Now, this UB section of serial size 305 by 165 by 40, this 40 is usually mass per meter. And the mass obviously is in kgs. Therefore, the mass of this UB section is 40 kilograms per meter. And for us to get moment, we are first of all going to calculate the value of the weight of this UB section. And weight is usually given by mass multiplied by gravity. And in this case, our mass is 40 kilograms per meter. We multiply by gravity, the force of gravity, which is 9.8 newtons per kg. We are going to get the weight in newtons. So we convert this weight into, we convert the weight from newtons to kilonewtons by dividing this by 1,000 or 10 raised to the power of -3. And by doing so, this is going to give us 0.392 kilonewtons. That is the weight. GK, remember, dead weight or dead rod should be multiplied by 1.4. Therefore, we are going to have 1.4 GK. And the weight is going to be 1.4 multiplied by the dead rod, which is GK of 0.392 kilonewtons. And by doing so, this is going to give us 0.5 kilonewtons. Therefore, from there, we can now determine the moment due to self-weight of this particular UB. And since self-weight is distributed throughout the entire beam section, the moment due to self-weight will be given by WL squared divided by 8. And therefore, this is going to be W, which is 0.5 kilonewtons, multiplied by L, which is the beam span, 9 squared, divided by 8. And by doing so, this is going to give us the moment of 5.6 kilonewton meter. So that is the moment due to self-weight of the beam, meaning that the total moment now is going to be the design moment of 429.3 kilonewton meter plus 5.6 kilonewton meter. This is going to give us a moment of 434.9 kilonewton meter. Therefore, that is the total moment. So when we actually compare the moment capacity and the total moment, we find that the moment capacity MC, which is a 459 kilonewton meter, is actually greater than the total moment, which is 434.9 kilonewton meter. It is greater than 434.9 kilonewton meter, and that means that the section we have selected is okay under moment. Then, after determining the value of the moment capacity and comparing with the total moment, we are now going to check the shear capacity of the composite section. So we go to shear capacity. And under shear capacity, we are going first of all to determine the shear force. So we go to the shear force. And in this case, shear force, which is Fv, will be given by WL divided by 2. And in this case, W is the design load, which we had gotten it as 42.4 kilonewton meter. So we have 42.4 multiplied by L, which is 9. That is the beam span. Then we divide this by 2. And that is going to give us a shear force of 190.8 kilonewtons. This shear force of Fv should be less than the shear resistance of the section. Therefore, we are going to determine the shear resistance. So we go to shear resistance. That is PV. And the shear resistance is usually given by this formula, 0.6 Py multiplied by Td, whereby Py is the design strength of our steel section. T is the thickness of the web of the steel section obtained from Appendix B, and D is the depth of fringe of our section. Therefore, the shear resistance PV will be equal to 0.6 multiplied by Py. The design strength of this steel is 355 newtons per square millimeter, since it is of grade S355. The thickness of the web from Appendix B is 6.1 millimeters, whereas the depth of the fringe from Appendix B is 303.8 millimeters. We are going to get the answer in newtons, and therefore we need to convert it to kilonewtons. So we divide all this by 1,000, since 1 kilonewton is equivalent to 1,000 newtons. And by doing so, this is going to give us a shear resistance of 394.7 kilonewtons. This shear resistance should be greater than the shear force, that is Fv. And we actually find that that is correct, since PV, which is 394.7, is greater than FV, which is 190.8 kilonewtons. And therefore, that means that the section we have selected is very much okay. After determining the value of the shear and comparing with the shear resistance, we are going now to check about the shear connectors. So we go to shear connectors. And under shear connectors, we are going to assume headed studs of 19 millimeters shank diameter by 100 millimeters height studs. And from table 4.18 of BS 5950, from table 4.18, such studs will have the characteristic resistance of of the said studs embedded in solid slab, that is QK 104 kilonewtons. 104 kilonewtons. That is the characteristic resistance of these studs. Therefore, the design strength of studs, design strength of the studs and a positive moment, that is QP, will be given by 0.8 QK. 0.8 QK. Therefore, design strength of the studs and a positive moment QP will be equal to 0.8 times QK, which is 104 kilonewtons, which is actually 83.2 kilonewtons. Then from there, we are going to determine the design strength of studs, design strength of studs embedded in a slab comprising of profiled metal decking, and concrete. So this is a QP prime, which will be given by K multiplied by QP, multiplied by QP. And in this case, the design strength of the studs will be equal to 0.8 multiplied by the QP that we have obtained up here of 83.2 kilonewtons. So multiplied by 83.2. And this is going to give us QP prime of 66.6 kilonewtons. After determining the design strength of the studs, we are now going to determine the total number of studs required. And the total number of studs required, total number of studs required will be given by RS divided by QP prime. And RS in this case is 1828.3 kilonewtons. So 1828.3 kilonewtons we divide by QP prime, which is 66.6 kilonewtons. And this is going to give us 27.5 studs. 27.5 studs.